Hey guys, how's it going? Mike coming back at you with another video on number theory. In the previous video, we saw some more advanced samples of congruences modulo n. In this video, we're going to take a look at binary and decimal representations of integers. So, a neat little fact that maybe you've thought of, maybe you haven't, but still a neat little fact that this video is sort of based upon is that we can represent any whole number whatsoever, any positive whole number, as a linear combination of powers of some fixed positive whole number n, such that the coefficients on those various powers of n, the coefficients are 0 through n minus 1. So I've provided a very basic sample here. The number 114. I can write 114 as a linear combination of the various powers of 4. And with every power of 4, the coefficient on that power of 4 is either 0, 1, 2, or 3. Again, 0 through n minus 1. My n value here is 4. So 114 is 2 times 1 plus 0 times 4 plus 3 times 16 plus 1 times 64. Or 2 times 4 to the 0 plus 0 times 4 to the 1 plus 3 times 4 to the 2 plus 1 times 4 to the third, or 4 cubed. And I could take 114, I could write it as a linear combination of powers of 5, of 10, of 14, 1000, whatever number I so chose. I could write 114 as some coefficient that is between or equal to 0 and n minus 1 times that fixed n raised to some power. Now, based on how small of an n value you pick and how large your number is, you may have to go to some high powers of n. Like, say I chose 50,000, and I wanted to write that as a linear combination of powers of 3, I may need to go to some pretty large powers of 3, like, say, 3 to the 9th, 3 to the 10th, perhaps even higher. But all of the coefficients on those powers of 3 will either be 0s, 1s, or 2s. So this is the general fact that this video is based on. We are going to examine the two most common cases, the case where n is 2 and the case where n is 10. So in the case where n is 2, you can write any integer b as a linear combination of powers of 2. So a naught times 2 to the 0 plus a1 times 2 to the 1 plus a2 times 2 squared plus a sub n times 2 to the n, where each of these a's here either have a value of 0 or 1. And based on this, we get the binary system. We've all heard of binary, at least I hope we have all heard of it. It's used in electronics, computers, websites, anything like that, anything with computers and internet and electronics and technology. Binary is all getting used. In electronics, a string of 8 bits is typically used, where the first number is the coefficient of the highest power of 2, which is going to be 2 to the 7th, or 128, and the last number is the coefficient of the lowest power of 2, which is 2 to the 0, or 1. So we have 2 raised to some power, 2 to the 7th, 2 to the 6th, 2 to the 5th, and then to the 4th, 3rd, 2nd, 1st, or 2 raised to the 0 power. We have 8 different powers of 2. And with those 8 powers of 2, I can represent the numbers 0 through 255 using the binary system. And we can write these numbers in binary. We can write any number between 0 and 255 as a sequence of 8 numbers, the numbers being either zeros or ones. And whether or not it's a 0 or 1 is determined by the coefficient on the power of 2. If the coefficient on the power of 2 is 1, then in binary we're going to write a 1. If the coefficient on the power of 2 is 0, then we write a 0. But here I have a sample here. The number 137. If we wanted to write this in binary, we first need to figure out how do we represent 137 as a linear combination of powers of 2. And we always write the largest power of 2, 2 to the 7th. We always write that first, and then we write 2 to the 0 last. So we go through our powers: 2 to the 7th, which is 128, 2 to the 6th, which is 64, 2 to the 5th, 32, so on and so forth, going down to 2 to the 0 or 1. And we say, okay, what are the coefficients on those powers of 2, such that when I add them up, I get 137. Well, 137 is 1 times 2 to the 7th, or 1 times 128, plus 0 times 2 to the 6th, plus 0 times 2 to the 5th, plus 0 times 2 to the 4th, plus 1 times 2 cubed. 2 cubed is 8, plus 0 times 2 squared, plus 0 times 2 to the 1, plus 1 times 2 to the 0. I have 128 and 8 and 1. Those add up to 137. So we take the coefficients 1, 0, 0, 0, 1, 0, 0, and 1. Those guys are the numbers I will write, and in the same order as my binary representation of 137. So righto there, that should be for 137. So because my coefficients went 1, 0, 0, 0, 1, 0, 0, 1, 137 in binary is 1, 0, 0, 0, 1, 0, 0, 1. And we can do this with any number between 0 and 255, including those guys as well. There are plenty of resources out there online to also look at how to determine the binary representation of a number between 0 and 255. So I'll let you look that up on your own. Now, what about, say, letters or capital letters or just other characters or symbols? We're just looking at this strictly in terms of numbers. There are things programmed and built into computers that deal with like an alternate binary kind of thing for dealing with those symbols and letters and the capital letters and all those kinds of things. But the other way that we can represent any integer is via the decimal system, or linear combinations of powers of 10. So b, any positive whole number, can be written as a naught times 10 to the 0, plus a1 times 10 to the 1, plus a2 times 10 squared, plus a sub n times 10 to the n, where each of these a's are 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And what those coefficients are called the digits of that number. That's nothing new. We're just looking at this in a slightly different context. So the other thing I want to just mention in this video, which is a neat little test that perhaps you haven't heard of. We know that there are tests to see if a number is divisible by 2 through 10. Some of them a bit harder to remember, some of them not. But what I want to show you is a test to see if a number is divisible by 11. Now, I've included in my notes here, I've included the facts that are sort of operating behind the scenes. These are the facts that let us say that this test works. And in previous times I've taught this course, I've gone through the proof of it. I'm not going to go through the proof of it this time. I'll let you read that on your own if you want to understand why the test is what that is. It's based on these two facts here. So if you want to take a look at the proof, read those two facts first. But here's the actual theorem or fact that describes the test for divisibility by 11. So we have our number capital N. It is in decimal representation. That is to say, linear combinations of powers of 10. So n a to the m, a sub m times 10 to the m, plus a sub m minus 1 times 10 to the m minus 1, plus a sub 1 times 10 plus a naught is the decimal representation of your number. And obviously all the a's are numbers 0 through 9, including 0 and 9 as well. Let capital T be a naught minus a1 plus a2 minus a3 plus negative 1 raised to the power m times a sub m. Now what this is it's the alternating sum, but the first term, the first number in the sum is the digit in your ones place. So it's digit in the ones place, minus digit in the tens place, plus digit in the hundreds place, minus digit in the thousands place. And you keep going on with that pattern until you've added or subtracted and or subtracted all of the digits, and you'll come up with some finite number. Then 11 divides n if and only if 11 divides t. So what this test is saying here is, let's go with the number 1,347 here. And we want to know, is this divisible by 11 or not? I'm going to start with the number in the tens place, in the ones place, 7. I'm going to then subtract the number in the tens place. Then I'll add the number in the hundreds place, and then I will subtract the number in the thousands place. So 7 minus 4 is 3, plus 3 is 6, minus 1 is equal to 5. And 5 does not, and 11 does not divide 5. So therefore, we would then automatically know that 1,347 is not divisible by 11. If I take a pretty nice sample here, 111,111, well, I'm doing number in the ones place minus the number in the tens place, plus a number in the hundreds, minus the number in the thousands. Continuing on with this right here. My apologies for that. Let's clean that up there. Minus 1, plus 1, minus 1. That's all equal to 0. And we know that 11 does indeed divide 0. So we would know that the number 111,111 is indeed divisible by 0. So that's just a fun little test, fun little thing just to toss out there. Nice to know. You can use this for, say, a quiz or test if you have to determine if a particular integer is prime or not. You can use this handy little test to see if the number is divisible by 11. In the next video, we are going to take a look at more linear congruences, but we'll be looking at congruence equations, things where we have to solve for the variable x. and we'll find that x is congruent to some number modulo some other positive integer n. If you have any questions or comments, be sure to drop them in the comments section below. Otherwise, until the next video, take it easy, guys.